Imagine two colossal giants drifting toward each other in the vast darkness of space. Silent, relentless, and inevitable. This isn't science fiction, it's the fate of our very own galaxy. The Milky Way and Andromeda, two of the largest galaxies in the cosmos, are on a collision course that will forever reshape the universe we call home. But what does this mean for Earth, for our solar system, and for the stars themselves? The answers lie in a cosmic journey, billions of years in the making. Two giant galaxies on a collision course. Imagine two ships crossing an endless sea of stars, slowly drifting toward each other over billions of years. The Milky Way, the galaxy we call home, is one of those ships. It's a barred spiral galaxy, its core illuminated by the glow of countless stars surrounding a supermassive black hole named Sagittarius A star. Measuring approximately 100,000 light-years in diameter and containing hundreds of billions of stars. On the other side of this cosmic dance lies Andromeda, our galactic neighbor. Also a spiral galaxy, Andromeda is larger than the Milky Way, spanning an estimated 220,000 light-years. It boasts nearly 1 trillion stars, many more than our galaxy, and has a bright, bustling core. Andromeda lies 2.5 million light-years away from us, a seemingly vast distance, yet within the grasp of gravitational pull over astronomical timescales. Together with the Milky Way and Andromeda forms part of the local group, a cluster of more than 50 galaxies bound by gravity. The local group is a microcosm of galactic interactions. Over time, smaller galaxies are drawn into larger ones, their stars and gas absorbed as part of an ongoing cosmic cycle. But now, the two giants of this cluster, the Milky Way and Andromeda, are inevitably being drawn toward one another. Galaxies colliding may sound dramatic, but in the vastness of space, it's surprisingly common. Across the observable universe, telescopes have captured countless examples of merging galaxies. These interactions are not sudden, violent crashes, but rather long, drawn-out encounters spanning hundreds of millions, even billions of years. Despite the universe expanding at an accelerating rate, objects within gravitationally bound systems, like the local group, don't drift apart. Instead, they are pulled together. Andromeda's approach toward the Milky Way is fueled by their mutual gravitational attraction and the invisible presence of dark matter. Vast halos of unseen mass surrounding both galaxies. Scientists have measured Andromeda's velocity relative to the Milky Way using precise instruments. Observations reveal it is closing the gap at approximately 110 kilometers per second, or roughly 400,000 kilometers per hour. While it may sound fast, the vast distance between us means the collision won't happen for another billions of years. But when it does, the result will be transformative. To understand the significance of the Milky Way-Andromeda collision, we must look at the broader role such events play in shaping the universe. Galaxies are not static objects. They are dynamic, evolving systems, constantly reshaped by internal processes and external interactions. Collisions are one of the primary mechanisms through which galaxies evolve. When galaxies collide, their stars rarely crash into each other directly. The vast distances between individual stars mean they simply pass by, but their collective gravitational forces create chaos. Gas clouds are compressed, sparking intense bursts of star formation. Stellar orbits are disrupted, creating new structures like elongated streams of stars or tidal tails. Over time, the distinct spiral arms of colliding galaxies may fade, merging into a single elliptical or lenticular galaxy. For the Milky Way and Andromeda, this collision will likely result in a new galaxy astronomers have already named Milkomeda or Milkdromeda. This newly formed galaxy will be larger, more massive, and likely elliptical in shape. Its structure will no longer resemble the elegant spirals we see today. The Milky Way and Andromeda are not isolated entities. They exist within the local group, a cluster of galaxies bound together by gravity. Beyond these two giants, the local group contains smaller galaxies like the Triangulum Galaxy M33 and dozens of dwarf galaxies, such as the Magellanic Clouds and the Andromeda satellites. these smaller galaxies play an essential role in the dynamics of the group. Over time, dwarf galaxies are often absorbed by larger ones in a process known as galactic cannibalism. The Milky Way has already consumed several smaller galaxies, and Andromeda is doing the same. The collision between the Milky Way and Andromeda will likely accelerate this process, as their combined gravitational pull draws in the remaining galaxies of the local group. Eventually, the local group may consolidate into a single massive structure. The inevitability of the Milky Way-Andromeda collision offers a unique opportunity for humanity, or whatever life forms exist in the future, to observe cosmic evolution on an unprecedented scale. Galactic collisions have happened countless times in the history of the universe, but this is the only one we can predict with certainty in our own cosmic neighborhood. It's a reminder that galaxies, like all things in the universe, are subject to change and transformation. Hubble and the soon-to-be-built James Webb Space Telescope are just two of the instruments that astronomers are using to examine Andromeda and the Milky Way as they slow-motion dance their way through creation and annihilation. Their research adds to our knowledge of the collision's trajectory and its possible consequences for the galaxy's stars, planets, and life forms. This cosmic event is more than a collision of matter and energy. It's a testament to the dynamic, ever-changing nature of the universe. In the face of such immense scales and forces, our existence on a small planet orbiting a single star becomes even more extraordinary. Galactic twins or cosmic opposites, the identities of the Milky Way and Andromeda. At first glance, the Milky Way and Andromeda seem like cosmic siblings, two massive spiral galaxies gracefully swirling through space, dominating the local group. But beneath the surface, these galactic giants tell vastly different stories. Let's dive into their fascinating quirks and contrasts, exploring what makes each galaxy so special. The Milky Way's spiral arms are like tightly knit highways bustling with activity. These well-defined structures, like the Perseus and Sagittarius arms, act as stellar nurseries where gas and dust come together to create new stars. Think of them as the galaxy's lifelines, brimming with energy and potential. Andromeda, by comparison, has spiral arms that are more like scattered pathways. They're less tightly wound, with gaps that suggest a history of turbulence. These fragmented arms hint at Andromeda's more chaotic interactions with smaller galaxies, which disrupted the smooth flow of its spiral structure. The differences in their arms paint a picture of two galaxies shaped by unique histories. Surrounding both galaxies are halos of ancient stars, but even these tell different tales. The Milky Way's halo stars are mostly metal-poor, which means they formed during a time when the universe lacked heavier elements like iron and carbon. This points to a relatively steady and calm growth for the Milky Way. Andromeda's halo, on the other hand, is more of a mixed bag. Its stars have a wider range of metallicities, suggesting a more colorful past filled with mergers and acquisitions. Each merger brought in stars with their own chemical fingerprints, creating a halo that serves as a patchwork quilt of Andromeda's dynamic history. The Milky Way and Andromeda each have their own neighborhoods, populated by smaller satellite galaxies. The Milky Way is home to the large and small Magellanic Clouds, two close companions that interact with its disk, feeding it gas and stars. These interactions help fuel ongoing star formation in the Milky Way. Andromeda, however, has a much larger entourage, boasting over 100 satellite galaxies. One standout is M32, a compact elliptical galaxy that's unusually dense. Its presence highlights Andromeda's gravitational might and its ability to absorb smaller galaxies over time. The differences in their satellite populations showcase how each galaxy has grown and shaped its surroundings. Globular clusters, tight groups of ancient stars, act as time capsules, preserving the early history of galaxies. The Milky Way has about 150 globular clusters, each more than 10 billion years old. These clusters provide insight into the galaxy's quiet but steady formation process. Andromeda outshines the Milky Way in this department. with nearly double the number of globular clusters. Some of these clusters are massive, hinting that they might be remnants of entire galaxies that Andromeda consumed. The sheer number and diversity of its clusters tell a story of a galaxy that's been far more aggressive in its cosmic conquests. Galactic magnetic fields are invisible yet crucial players in shaping the behavior of galaxies. The Milky Way's magnetic field is well structured and large-scale, helping guide cosmic rays and influence the motion of gas and dust. This structured field may even play a role in stabilizing its spiral arms. Andromeda's magnetic field, however, is weaker and more chaotic. It's likely been disrupted by the galaxy's history of mergers and interactions. Without the same stabilizing influence, Andromeda's arms and interstellar medium have evolved in a more haphazard way. The gas composition of the Milky Way and Andromeda offers another point of contrast. The Milky Way's interstellar medium, ISM, has a balanced mix of neutral hydrogen and ionized gas, supporting consistent star formation. Andromeda, on the other hand, has a higher proportion of ionized hydrogen, which could explain its less active star-forming regions. The differences in their gas compositions also hint at their histories of supernova activity. Andromeda may have gone through intense bursts of star formation and subsequent supernova explosions, enriching its ISM with heavy elements and shaping its current state. Both galaxies bear the marks of their past gravitational encounters in the form of tidal streams. The Milky Way is currently in the process of absorbing the Sagittarius dwarf galaxy, creating looping streams of stars visible across its halo. These stellar streams serve as direct evidence of the Milky Way's ongoing evolution. Andromeda has its own tidal features, including arcs and loops of stars that trace back to galaxies it devoured. These structures are more prominent and widespread, again pointing to Andromeda's more aggressive growth through mergers. At the centers of these galaxies lie their bulges, which reveal much about their internal dynamics. The Milky Way's bulge is boxy and elongated, shaped by the interaction between its central bar and spiral arms. This suggests a dynamic and evolving core. Andromeda's bulge, by contrast, is more spherical and classical, reflecting a history with fewer internal disturbances. Its shape indicates a core that's remained relatively stable over billions of years, despite the galaxy's tumultuous outer regions. The rotation rates of the Milky Way and Andromeda provide clues about their mass and dark matter content. The Milky Way's stars orbit its center at about 220 km per s, while Andromeda's stars move even faster, at 250 km per s. This difference suggests that Andromeda may have a more massive halo of dark matter, or a different distribution of its mass. These subtle differences in rotational dynamics hint at the unseen forces that govern both galaxies. The stars within these galaxies also reflect their current stages of evolution. The Milky Way is still actively forming stars, supported by a healthy supply of gas and dust. Its stellar population includes a mix of young, middle-aged, and older stars. Andromeda, on the other hand, appears to be winding down. It has a higher proportion of older stars, indicating that its star formation rate has slowed. This contrast offers a snapshot of two galaxies at different points in their life cycles, one still bustling with activity, the other beginning to settle. The galactic ecosystem, interactions beyond the stars. Interstellar gas and dust play pivotal roles, shaping the dynamics of galaxies like the Milky Way and Andromeda. When galaxies interact, they exchange materials, often redistributing molecular clouds that fuel star formation. These interactions are not merely collisions. They are a fundamental aspect of the galactic ecosystem, constantly recycling and redistributing resources. When galaxies like the Milky Way and Andromeda draw closer, their ecosystems begin to interact even before a physical collision. Gas reservoirs are disturbed, creating turbulent flows that ignite bursts of star formation in regions where gas density increases. Observations of other merging galaxies reveal that this influx of material often triggers starburst activity, producing stars at a rate far higher than usual. However, not all regions benefit equally. While some areas see an abundance of new stars, others are stripped of their star-forming material, leaving them barren. Giant molecular clouds, GMCs, the nurseries of stars, play a critical role in these processes. During a galactic interaction, GMCs may compress and form clusters of new stars or dissipate entirely due to the gravitational chaos. In some cases, these clouds survive the turmoil, preserving potential for future star formation. The fate of these clouds determines how a galaxy evolves after an encounter, whether rejuvenated with new stars or depleted of its lifeblood. Galaxies are master recyclers, constantly redistributing elements through their ecosystems. Supernovae, the explosive deaths of massive stars, inject heavy metals into the interstellar medium, enriching gas clouds with the ingredients needed for new stars and planets. These enriched clouds, in turn, fuel the formation of next-generation stars, creating a cycle that sustains galactic ecosystems. When galaxies merge, this recycling process accelerates as gas clouds mix and interact, producing regions of intense enrichment that may host new planetary systems. Evidence from interstellar gas clouds shows that materials from ancient stars can persist in the ecosystem for billions of years, seeding future generations of celestial objects. This cosmic recycling ensures that even in the wake of destruction, galaxies sow the seeds for new life and structure. Galactic interactions often disturb the flow of gas within and between galaxies. The Milky Way and Andromeda, for example, are surrounded by vast halos of diffuse gas that will interact long before the galaxies themselves collide. Observations of other galactic pairs show that these halos can form bridges of gas, creating connections that allow material to flow between galaxies. This exchange enriches both systems, fueling star formation and altering the dynamics of their ecosystems. As galaxies merge, energy dissipation becomes a critical factor. The kinetic energy from their motions is converted into heat, radiating outward and influencing the intergalactic medium. These feedback loops create a complex dance of energy that shapes not only the merging galaxies, but also the space around them. Some of this energy may even escape into the broader cosmos, affecting nearby galaxies and clusters. The effects of a merger between the Milky Way and Andromeda will not be confined to these two giants. Smaller galaxies in the local group, such as the Triangulum galaxy, will also feel the impact. These satellite galaxies contribute material to the larger systems, while also being shaped by the gravitational forces of the merger. Observations of similar systems suggest that smaller galaxies often experience bursts of star formation or structural distortions during such interactions. Additionally, interactions between the galactic halo and interstellar medium influence smaller satellite galaxies. Gas stripped from these satellites can be absorbed into the larger systems, enriching their ecosystems while depleting the smaller ones. These exchanges highlight the interconnectedness of galaxies, where no system exists in isolation. Galactic collisions often produce phenomena that are not visible in isolated systems. Shock fronts, for example, emerge as gas clouds collide at high speeds, creating luminous regions that can stretch across thousands of light years. These shock fronts compress gas, potentially forming new stars, or revealing hidden reservoirs of material that were previously undetectable. Another fascinating phenomenon is the emergence of gas rings, luminous structures formed when the gravitational dynamics of merging galaxies compress gas into circular patterns. These rings often serve as regions of intense star formation, providing a spectacular visual representation of the ecosystem's complexity. Such unique events offer a glimpse into the dynamic processes at play during galactic interactions. Galactic mergers can also influence the formation and distribution of planetary systems. Molecular clouds redistributed during the merger create new opportunities for planets to form around young stars. However, the chaotic nature of these interactions can also eject planets from their systems, turning them into rogue worlds wandering the cosmos. These rogue planets, untethered to any star, are a testament to the unpredictable outcomes of galactic ecosystems in flux. Shocks within the galactic medium can also impact the disks of young stars, potentially accelerating or hindering planet formation. The creation of new planetary systems during a merger adds another layer of complexity to the ecosystem, where destruction and creation coexist. By studying other galaxies undergoing similar interactions, astronomers gain valuable insights into the future of the Milky Way and Andromeda. Observations of distant ecosystems reveal patterns and phenomena that inform our understanding of galactic evolution. For instance, the antennae galaxies, a pair of merging systems, show how gas flows and star formation peaks during specific stages of the interaction. These examples provide a roadmap for predicting what may happen during and after the Milky Way-Andromeda merger. In addition to direct observations, simulations of these ecosystems allow scientists to test hypotheses about how gas, energy, and material are redistributed. These models help refine our understanding of the dynamic processes that shape galaxies, offering a glimpse into the broader universe's ecosystem. As the Milky Way and Andromeda approach their inevitable collision, their ecosystems are already beginning to change. The halos of gas surrounding both galaxies are likely interacting, setting the stage for future exchanges of material. Predictions suggest that this pre-collision phase will trigger subtle changes in star formation rates and gas dynamics, paving the way for more dramatic transformations. After the merger, the combined galaxy will host a new ecosystem, shaped by the redistribution of gas, stars, and energy. This transition will likely produce regions of intense activity alongside areas of relative quiet, reflecting the diversity and resilience of galactic ecosystems. Tracing Andromeda's path, a galactic journey toward collision. One of the most fundamental tools for understanding Andromeda's motion is the Doppler effect, which allows astronomers to analyze how light from the galaxy shifts as it travels through space. Andromeda's distinct blue shift, an indication that its light waves are compressed, offers clear evidence of its approach. Unlike the majority of galaxies observed to be receding due to the universe's expansion, Andromeda is an outlier, drawn toward us by mutual gravitational attraction. This early discovery provided the first clue that our neighboring giant was not just moving through the void, but on a direct course to meet the Milky Way. Measuring Andromeda's radial velocity, its speed along the line of sight, is relatively straightforward, but determining its transverse motion, or sideways drift, is far more complex. Over decades, astronomers have tracked Andromeda's position against background stars, using astrometric techniques to estimate its lateral movement. This data, combined with knowledge of gravitational interactions within the local group, refines predictions about the timeline and nature of the impending collision. Though the transverse motion is subtle, it significantly impacts models of how the galaxies will merge and what the resulting structure will look like. Andromeda's path through the local group, our cosmic neighborhood, is far from linear. The local group consists of over 50 galaxies, including the Milky Way, Andromeda, the Triangulum galaxy, and numerous dwarf galaxies. Together, these galaxies form a gravitationally bound cluster, with Andromeda and the Milky Way as the dominant members. The intricate gravitational pulls between these entities shape their movements. For example, smaller galaxies like the Triangulum galaxy exert subtle forces on Andromeda, while Andromeda, in turn, influences their trajectories. These interactions create a dynamic web of motion, ensuring that Andromeda's approach is a carefully choreographed dance influenced by every nearby mass. Understanding Andromeda's mass is crucial for accurate modeling of its trajectory. Estimates of its total mass, including its visible stars, interstellar gas, and elusive dark matter, vary. Observations suggest Andromeda might be slightly more massive than the Milky Way, with differences in their dark matter halos complicating direct comparisons. Refining these mass estimates is essential because the gravitational pull between two galaxies is directly proportional to their combined mass. Advanced techniques such as gravitational lensing, observing how light bends around Andromeda, help astronomers better understand its mass distribution. The intergalactic medium, IgM, surrounding Andromeda subtly shapes its journey. This vast expanse of ionized hydrogen and other particles creates a drag effect on galaxies moving through it. Although the IgM is incredibly diffuse, its cumulative effect over billions of years slightly slows Andromeda's motion. The density of the IgM is not uniform, with variations creating regions of higher resistance. These interactions, though minimal, add a layer of complexity to Andromeda's trajectory, subtly altering its path toward the Milky Way. The structure of Andromeda itself also reveals clues about its journey. Its majestic spiral arms, sprawling extensions of stars and interstellar material, rotate around a dense central bulge. By studying the motion of these arms relative to the galaxy's core, astronomers gain insights into the forces acting on Andromeda as it travels. The rotational dynamics of these spiral arms, influenced by gravitational interactions within the local group, reflect the forces shaping Andromeda's movement. Starburst regions within Andromeda offer additional insights. These pockets of intense star formation are often triggered by gravitational interactions with smaller galaxies or interstellar clouds. Observing the distribution and activity of these regions allows scientists to reconstruct Andromeda's recent history of interactions, shedding light on how past events influence its current trajectory. For instance, recent bursts of star formation may indicate encounters with satellite galaxies that added momentum or altered its path. Speaking of satellites, Andromeda's companion galaxies, such as M32 and M110, play a significant role in its journey. These smaller galaxies orbit Andromeda, exerting gravitational forces that influence its structure and motion. These interactions are a two-way street. While the satellites shape Andromeda's trajectory, they are also affected by Andromeda's gravitational pull, often leading to distortions or tidal stripping of their stars and gas. These dynamics will also factor into the final stages of the collision, adding their mass and momentum to the mix. Computer simulations have become indispensable in visualizing Andromeda's journey. These models incorporate vast amounts of data, including mass estimates, velocity measurements, and gravitational interactions within the local group. Advanced simulations predict the collision's timeline, likely occurring in 4-5 billion years, and its stages, from the initial approach to the eventual formation of a new merged galaxy. These visualizations not only provide a glimpse into the future, but also help refine our understanding of the complex forces at play. Beyond the local group, Andromeda's path is shaped by larger cosmic structures. The galaxy exists within the cosmic web, a vast network of filaments and voids formed by dark matter and intergalactic gas. As Andromeda moves through this web, the gravitational pull of distant structures subtly influences its trajectory. This broader context connects Andromeda's journey to the larger-scale evolution of the universe, demonstrating how local events are tied to cosmic dynamics. Andromeda's gaseous halo, an enormous envelope of diffuse gas extending far beyond the visible galaxy, adds another layer of complexity. This halo overlaps with the Milky Way's halo, creating regions of interaction that are already occurring long before the galaxies collide. These interactions, ranging from the gentle mixing of gases to more energetic phenomena, provide a preview of the eventual merger. Observing these halos offers critical insights into the early stages of galactic collisions. Ancient globular clusters within Andromeda also serve as markers of its journey. These dense collections of stars, formed during the galaxy's early years, are relatively unaffected by internal galactic dynamics. Tracking their positions and velocities provides a stable reference point for understanding Andromeda's motion over billions of years. These clusters, remnants of the galaxy's formation, tell a story of continuity amid change. Observational data is at the heart of Andromeda's study. Instruments like the Hubble Space Telescope have provided precise measurements of its motion and structure, while upcoming telescopes like the Nancy Grace Roman Space Telescope promise even greater detail. These observations refine our models and reduce uncertainties, ensuring that our predictions about Andromeda's path are as accurate as possible. Andromeda's journey is not just a product of current forces, but a narrative shaped by billions of years of cosmic history. Events such as early galaxy mergers, interactions with the cosmic web, and encounters with satellite galaxies all leave imprints on its motion. Understanding these past influences adds depth to our understanding of its future path, connecting the present to the universe's dynamic history. Each force, interaction, and structure contributes to this grand narrative, illustrating the intricate choreography of galaxies across billions of years. Galactic cannibalism, a common cosmic phenomenon. Our home galaxy, the Milky Way, is an active participant in this cosmic drama. Perhaps the most well-documented example of its appetite is the ongoing consumption of the Sagittarius dwarf galaxy. This smaller elliptical galaxy has been torn apart by the gravitational forces of the Milky Way. Tidal forces, caused by the difference in gravitational pull on the near and far sides of the galaxy, stretch and shred it, creating long streams of stars that now arc through the Milky Way's halo. Data from the Gaia Space Telescope has provided stunning maps of these star streams, allowing us to trace the movement of Sagittarius's remnants with remarkable precision. These streams are more than just evidence of the Milky Way's predatory nature. They are relics of the galaxy's past interactions, clues to its growth and evolution. Andromeda, the Milky Way's larger and more massive sibling, has an even more dramatic history of cannibalism. Observations reveal vast stellar streams surrounding Andromeda, remnants of galaxies it has consumed over time. The giant stellar stream, a prominent feature, is thought to be the remains of a smaller galaxy Andromeda devoured billions of years ago. These streams act as fingerprints, preserving the legacy of past victims. Simulations suggest that Andromeda's size and structure are direct results of its cannibalistic history. Unlike the Milky Way, which still maintains its defined spiral arms, Andromeda's structure shows signs of past turbulence and disruption, a testament to the chaotic meals it has consumed. The mechanism driving galactic cannibalism lies in the powerful tidal forces generated during close encounters. As a smaller galaxy approaches a larger one, gravitational forces pull on its stars and gas, creating dramatic tidal streams. These streams are not just theoretical constructs. They are visible evidence, captured by telescopes as arcs of light stretching across space. Tidal forces don't merely disrupt smaller galaxies. They also shape the larger galaxies they interact with. The inflow of stars and gas can fuel starburst activity, where galaxies experience intense periods of star formation. The result is not destruction, but transformation, a dance of creation and reconfiguration on a galactic scale. The current situation with the Sagittarius dwarf galaxy is one of the most fascinating cases of galactic cannibalism. This elliptical galaxy is currently undergoing galactic absorption after having previously existed independently. Stars from it are being sucked into the Milky Way's halo and disk as it finishes its death spiral. This merger is not just an academic curiosity, it has had profound effects on the Milky Way itself. The inflow of stars and gas has triggered waves of star formation, reshaping parts of the galaxy. In a way, the Sagittarius dwarf galaxy lives on, its remnants integrated into the structure of the Milky Way, a part of its continuing evolution. The Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, are likely to meet a similar fate. For now, they remain gravitationally bound to the Milky Way, but simulations predict that over billions of years, their orbits will decay. Eventually, they too will be pulled apart by tidal forces and absorbed. The Magellanic Clouds are not just passive companions, they are actively contributing to the Milky Way's growth. Streams of gas, known as the Magellanic Stream, flow from these galaxies, providing raw material for future star formation. The clearest evidence of galactic cannibalism lies in the stellar streams that crisscross the halos of galaxies. These streams are the remnants of smaller galaxies, torn apart by tidal forces and stretched across the sky. In the Milky Way, Streams like the Helmy Stream and the Orphan Stream serve as records of past mergers. These streams are not just beautiful, they are scientifically invaluable. By studying their motion and composition, astronomers can reconstruct the histories of the galaxies they once belonged to, piecing together the Milky Way's long history of growth through consumption. Andromeda's halo is even more extensive than that of the Milky Way, spanning millions of light-years and encompassing countless stellar streams. This halo is a treasure trove of information, revealing the remnants of Andromeda's past mergers. Observations suggest that Andromeda has consumed dozens of smaller galaxies, each contributing to its growth and shaping its structure. Galactic cannibalism is not limited to isolated interactions. It is a fundamental part of the cosmic web, the large-scale structure of the universe. Galaxies are connected by filaments of dark matter, gas, and stars, which guide smaller galaxies toward larger ones. These filaments serve as highways, facilitating the flow of material and enabling the hierarchical growth of galaxies. Many massive elliptical galaxies are the end products of repeated cannibalism events. Unlike spirals, which retain their defined arms, ellipticals are featureless, with stars evenly distributed in a spheroidal shape. This homogeneity is the result of multiple mergers, where the chaotic inflow of stars smooths out the structure. The transformation from a spiral to an elliptical galaxy represents the final stage of galactic evolution, a process driven by cannibalism. The drama of galactic cannibalism is not unique to the Milky Way and Andromeda. Observations of distant galaxies reveal similar processes playing out across the cosmos. The antennae galaxies, for example, are in the midst of a merger, their tidal tails stretching across hundreds of thousands of light-years. Galactic cannibalism may sound violent, but it is a natural and essential process in the life cycle of galaxies. It enriches larger galaxies with new stars, gas, and dark matter, fueling their growth and shaping their evolution. Without it, the universe would look very different, with fewer large galaxies and less complexity in their structures. The Milky Way, Andromeda, and countless other galaxies are not static entities. They are dynamic, ever-changing systems, constantly interacting with their environments. Galactic cannibalism is a reminder of the universe's intricate balance, a cosmic interplay of destruction and creation that defines the evolution of galaxies. What happens during a galactic collision? Galactic collisions unfold over billions of years in distinct phases. The journey begins with the initial approach, when two galaxies are drawn together by their mutual gravitational pull. As they edge closer, tidal forces come into play, stretching and distorting their structures. This phase is marked by the first visible disruptions, such as elongated arms and streams of stars being pulled outward. The next stage is interpenetration, where the galaxies begin to pass through each other. This is a phase of immense dynamism. Stars, though abundant, are separated by such vast distances that direct collisions between them are exceedingly rare. Instead, their trajectories are altered by the gravitational chaos. Gas and dust clouds, however, are not so lucky. They collide and compress, triggering intense waves of star formation in a phenomenon known as a starburst. Finally, over hundreds of millions of years, the galaxies enter the final merger stage. By this time, their original forms are all but unrecognizable. What remains is a single, larger galaxy, its stars and gas redistributed into a new, often elliptical structure. This process, while seemingly destructive, is also creative, giving birth to new stars and reshaping the universe one collision at a time. The driving force behind every galactic collision is gravity. Galaxies are held together by their gravitational pull, and the same force dictates their interactions. When two galaxies encounter one another, their gravitational fields overlap, creating a tug-of-war that reshapes their trajectories and internal structures. Stars and gas are drawn out into tidal tails, which can stretch for hundreds of thousands of light-years, forming some of the most striking features observed in merging galaxies. Gravity also governs the eventual merging of the galaxy's central supermassive black holes. These massive objects, each millions or billions of times the mass of our Sun, begin a slow but inevitable dance. Over time, they spiral closer together, emitting powerful gravitational waves before merging into a single, even larger black hole. The rarity of star collisions as a galactic collision mechanism is one of the biggest surprises. Even though galaxies have billions of stars, they whiz by one another without colliding due to the enormous distances between them. Picture two swarms of bees gliding by each other. The bees in each swarm communicate with each other, but they mostly stay out of each other's way. What does change, however, are the orbits of these stars. The gravitational forces at play can eject stars into intergalactic space or push them into new, more elliptical orbits within the merging galaxy. Some stars may even end up in the stellar halo, a diffuse, spherical region surrounding the galaxy. While stars avoid collision, gas clouds do not. When these clouds meet, they collide at high speeds, compressing the material within them. This compression triggers starburst activity, a rapid phase of star formation. Massive, short-lived stars form in these regions, shining brightly and contributing to the galaxy's luminosity. Starburst activity also significantly affects the chemical evolution of the galaxy. The newly formed stars quickly burn through their nuclear fuel and end their lives in spectacular supernova explosions. These supernovae enrich the surrounding gas with heavy elements, seeding the galaxy with the building blocks for future generations of stars and potentially habitable planets. At the heart of most galaxies lies a supermassive black hole, and during a collision, these titanic objects play a central role. Initially, the black holes remain at the centers of their respective galaxies. As the galaxies merge, their cores, along with the black holes, are drawn together. Eventually, the black holes themselves begin to spiral toward one another. When these black holes merge, they emit ripples in the fabric of spacetime that can travel across the universe. These events are some of the most powerful sources of gravitational waves ever detected and offer astronomers a unique glimpse into the dynamics of black holes and the fundamental physics of the cosmos. As the gas in colliding galaxies compresses and forms new stars, the intense energy output from these regions can drive powerful galactic winds. These winds, propelled by supernova explosions and the radiation pressure from massive stars, can expel gas and dust into intergalactic space. While this process can temporarily halt star formation by depleting the galaxy of gas, it also spreads heavy elements into the surrounding environment, enriching the intergalactic medium. Over time, this feedback loop helps regulate the pace of star formation and shapes the evolution of the galaxy. The galaxies involved undergo fundamental form changes as they collide with one another. While merging, spiral galaxies like Andromeda and the Milky Way often take on a more elliptical form, losing their distinctive spiral arms in the process. As a result of the redistribution of gas and stars caused by the gravitational forces, this change takes place. In some cases, the resulting galaxy may have an irregular shape, especially in the intermediate phases of the collision. Over billions of years, however, the galaxy settles into a new equilibrium, often resembling a giant elliptical galaxy. Galactic collisions are slow-motion events, unfolding over billions of years. From the initial approach to the final merger, the entire process spans a timescale that dwarfs human history. Even the most dramatic phases, such as interpenetration and starburst activity, can take hundreds of millions of years to play out. This immense time frame offers astronomers a unique opportunity to study collisions at different stages. By observing galaxies at various points in their interactions, scientists can piece together a comprehensive picture of the processes involved. Colliding galaxies are some of the most luminous objects in the universe. The combination of starburst activity, supernovae, and active galactic nuclei creates a brilliant display of light and energy. This luminosity makes galactic collisions relatively easy to observe, even from vast distances. Examples like the antennae galaxies and the mice galaxies provide vivid snapshots of galaxies in the throes of merging. These observations not only showcase the beauty of these events, but also offer invaluable data for understanding the underlying physics. The future shape of the Milky Way Andromeda merger. In about 4 to 5 billion years, the Milky Way and Andromeda will no longer exist as we know them. Instead, they will combine to form a single, massive galaxy. Scientists have even given this future entity a name, Milkomeda, a fusion of the Milky Way and Andromeda. This name reflects not only the unification of two great galactic giants, but also the awe and wonder of humankind in observing and attempting to understand the forces shaping the universe. Today, both the Milky Way and Andromeda are magnificent spiral galaxies, their arms sprawling outward in delicate yet structured formations. But this iconic shape will not survive the merger. As the two galaxies begin their dance of destruction and creation, gravitational forces will wreak havoc on their spirals, twisting and stretching them beyond recognition. Over time, the organized rotation of the stars and gas in the spirals will give way to random chaotic motions. The result will be a galaxy with a more spherical or elliptical shape, a hallmark of galactic mergers observed throughout the cosmos. The elegant spiral arms of the Milky Way, which house countless stars, planets, and potentially life itself, will be among the first casualties of this cosmic collision. The gravitational disruptions of Andromeda's approach will tear apart these structures, dispersing their stars into new, chaotic orbits. Andromeda's own spiral arms will suffer a similar fate, their graceful structure obliterated as the galaxies begin to merge. Andromeda's sheer size and mass will play a dominant role in shaping the new galaxy. With roughly 1 trillion stars compared to the Milky Way's estimated 200–400 billion, Andromeda brings significantly more material into the mix. Its gravitational influence will likely dictate much of the merger's dynamics, steering the Milky Way's stars and gas into new configurations. At the heart of this transformation lies a spectacular event, the merging of the two supermassive black holes currently residing at the centers of the Milky Way and Andromeda. These black holes, each millions of times the mass of our Sun, will gradually spiral toward one another, radiating gravitational waves as they do. When they finally collide and merge, they will form a single, even more massive black hole. This newly formed black hole will anchor the core of Milkomeda, likely surrounded by a dense cluster of stars and gas. Despite the apparent violence of this collision, individual stars are unlikely to collide. The vast distances between stars mean that they will mostly pass by one another like ships in the night. However, their orbits will be profoundly affected. Some stars will be flung outward into the galaxy's outskirts, forming an extended halo. Others will be drawn closer to the core, contributing to the dense central region of Milkomeda. The resulting galaxy will no longer have the neat circular orbits characteristic of spirals, but will instead feature stars moving in every direction, creating the chaotic structure of an elliptical galaxy. For those wondering about the future of our solar system, the answer is both fascinating and uncertain. As Andromeda approaches, the Milky Way stars, including our Sun, will be scattered into new orbits. The solar system could find itself ejected into the galaxy's outskirts, or even into intergalactic space. Alternatively, it might settle into a stable orbit within the new galaxy. In either case, the night sky would change dramatically, with unfamiliar constellations and a far more chaotic stellar landscape. In the long term, Milkomeda will transition into what astronomers call a red and dead galaxy. With its gas reserves exhausted, new star formation will cease, and the galaxy will slowly dim over billions of years. The vibrant blue light of young stars will give way to the cooler red light of older stars, leaving behind a galaxy populated by ancient stellar remnants. To understand what Milkomeda might look like, astronomers study other galactic mergers happening across the universe. Observations of galaxies like the antennae galaxies, which are in the process of merging, provide a glimpse of the chaotic beauty of these cosmic events. Simulations of other elliptical galaxies, believed to have formed through mergers, offer additional insights into the eventual fate of the Milky Way and Andromeda. The Milky Way and Andromeda are not isolated in their journey toward one another. They are part of a collection of galaxies known as the local group, which includes dozens of smaller galaxies. Some of these may be drawn into the merger, either becoming part of Milky or being flung into new trajectories. The gravitational landscape of the local group will be forever altered by this event. If humans or their descendants are still around billions of years from now, they will witness one of the most extraordinary sights in the universe. As Andromeda approaches, it will appear as a massive, glowing structure in the night sky, eventually spanning the horizon. The final stages of the merger will bring about a sky filled with brilliant star clusters, glowing gas clouds, and an active galactic core. The Milky Way-Andromeda collision is not an isolated event, but part of the broader story of cosmic evolution. Galaxy mergers are a natural outcome of gravitational interactions within clusters and groups of galaxies. Understanding this process helps scientists piece together the history of the universe and predict its future. The Milky Way-Andromeda merger is just one chapter in the ongoing story of galactic life cycles. The impact on the solar system. Currently, the Sun orbits around the center of the Milky Way at a comfortable distance of about 27,000 light-years, completing a galactic lap every 230 million years. But when Andromeda and the Milky Way collide, this familiar orbit will likely be disrupted. The gravitational forces unleashed by the merger will fling stars, including the Sun, into new trajectories. Simulations suggest that the solar system could be ejected from its current orbit and sent spiraling toward the outskirts of the newly merged galaxy, Milky Way, or possibly even into intergalactic space. While the solar system is expected to remain intact, its place in the cosmos may look vastly different. This displacement might move the solar system into a region teeming with new stars, or scatter it into a quieter, more remote corner of the galaxy. If it finds itself near the galactic core, the heightened stellar density and activity could expose Earth to increased levels of cosmic radiation, a dramatic shift from the relatively peaceful neighborhood we inhabit today. One of the most captivating changes for any future observers on Earth will be the transformation of the night sky. As Andromeda approaches, it will gradually grow larger, eventually dominating the celestial dome with its dazzling spiral structure. Over millions of years, the skies will transition from the familiar Milky Way band stretching across the horizon to a chaotic, glowing spectacle of colliding stars, gas, and dust. As the two galaxies merge, the stars will dance in intricate gravitational patterns. Although individual stars are unlikely to collide due to the vast distances between them, the interplay of their light will create unprecedented celestial displays. Earth's night sky will become a living tableau filled with supernovae, star-forming regions, and the brilliant glow of the merging galactic cores. The outermost reaches of the solar system, home to the Oort cloud, will not escape the effects of the collision. This spherical shell of icy bodies, stretching nearly 2 light-years from the Sun, is delicately balanced by the gravitational pull of the Milky Way. The gravitational disruptions caused by Andromeda's approach could send shockwaves through the Oort cloud, dislodging countless comets and flinging them toward the inner solar system. This cascade of icy travelers could result in a dramatic increase in cometary impacts on Earth and other planets. While such impacts have historically played a role in shaping Earth's evolution, delivering water and organic compounds, a sudden surge in collisions could pose existential risks for life. These events would create a cosmic fireworks display, but come with potentially catastrophic consequences. As Andromeda's stars intermingle with those of the Milky Way, the likelihood of close stellar encounters increases. a passing star, could exert enough gravitational influence to perturb the solar system's stability. For instance, the orbits of planets could shift slightly, and objects in the asteroid belt or Kuiper belt might be redirected toward the inner solar system. However, close encounters with stars could also have positive outcomes. A nearby star-forming region might provide new materials or energy sources for exploration and observation. Such encounters might even bring Earth closer to habitable exoplanets, sparking unprecedented opportunities for interstellar exploration. The merging may cause cosmic radiation to rise, which is one of the major problems it poses. There will be additional pressure on Earth's magnetosphere to protect the planet from high-energy particles when the solar system travels through Milky Way's more active or heavily inhabited areas. The ozone layer and all forms of life on Earth may be jeopardized if the sky were to become too irradiated with high quantities of cosmic radiation. In this new cosmic environment, humanity might have to innovate to mitigate these dangers. Advanced technologies could be developed to shield habitats or terraform parts of Earth's surface to maintain habitability. By the time the Milky Way and Andromeda fully merge, the Sun will be nearing the end of its life cycle, transitioning into a red giant. This phase will cause the Sun to expand, potentially engulfing Mercury, Venus, and possibly even Earth. The merger might not directly influence this process, but the changes in the solar system's galactic environment could affect the Sun's evolution. If Earth survives the Sun's red giant phase, its altered galactic position could expose it to new cosmic phenomena such as gamma-ray bursts or supernovae. These events could further challenge the planet's long-term habitability. If humanity endures long enough to witness the Milky Way-Andromeda collision, our species may play an active role in navigating its consequences. Advanced spacefaring civilizations could engineer solutions to protect Earth or migrate to safer regions of the galaxy. The collision might also inspire a renewed focus on interstellar exploration, pushing humanity to establish colonies on distant exoplanets. The new galactic landscape of Milkomeda, with its blend of Milky Way and Andromeda stars, could serve as the backdrop for humanity's next great chapter. The collision would not just be a cosmic event, but a profound opportunity for scientific discovery, cultural evolution, and the expansion of human potential. The role of gas and star formation in the collision. As the Milky Way and Andromeda draw closer, their massive gas clouds, primarily hydrogen and helium, will begin to interact long before the stars of each galaxy ever cross paths. These interactions occur in the form of shock waves and turbulence, created as the gravitational forces of the galaxies compress and heat the interstellar medium. In the early stages, the gas from both galaxies will collide, producing regions of intense compression where molecular clouds are forced into smaller volumes. These dense pockets of gas serve as the perfect conditions for the birth of stars. The interaction zones, where gas clouds overlap, become galactic nurseries, hosting rapid and prolific star formation. The gas compression during the Milky Way-Andromeda collision will give rise to a population of hot, young, and massive stars. These newly formed stars, while short-lived, will burn brightly, releasing vast amounts of ultraviolet radiation and stellar winds into their surroundings. These energetic outputs will further shape the gas clouds, pushing them outward and possibly triggering additional waves of star formation in adjacent regions. Massive stars formed during this phase are also key contributors to the chemical evolution of the galaxy. As they explode as supernovae, they enrich the surrounding gas with heavy elements like carbon, oxygen, and iron. This enriched material forms the building blocks for future generations of stars and potentially planets, carrying the legacy of the collision into the future. Shockwaves generated by the collision play a pivotal role in sculpting the interstellar medium. When gas clouds collide at high velocities, the resulting shock compresses the gas into dense filaments or clumps, the precursors to star formation. These shock waves, which can propagate across vast stretches of the galaxy, act as triggers, initiating star formation in regions that were previously dormant. The energy from these shock waves doesn't just stop at forming stars. It also heats up parts of the interstellar medium, creating vast bubbles of hot ionized gas. These bubbles, observed in other merging galaxies, become prominent features, marking regions of intense activity and transformation. The newly formed stars begin to exert feedback on their environment. Stellar winds from massive stars, combined with the energy from supernova explosions, create powerful galactic winds. These winds can blow gas outward, dispersing it into intergalactic space or distributing it unevenly throughout the merging galaxies. Feedback effects from starburst regions also play a regulatory role. While they trigger additional waves of star formation in some areas, they can also suppress it in others by heating or dispersing gas. This dual role ensures that the galaxy evolves in a dynamic yet balanced manner, shaping the final outcome of the merger. At the centers of both the Milky Way and Andromeda lie supermassive black holes, which will become significant players during the collision. As gas is funneled toward the cores of the merging galaxies, it will spiral into these black holes, forming massive accretion disks. The process of accretion releases enormous amounts of energy in the form of radiation, potentially transforming the black holes into active galactic nuclei, AGN. Active galactic nuclei, observed in other merging galaxies, emit intense X-rays and ultraviolet light, capable of affecting the surrounding gas on a galactic scale. This radiation can ionize gas, making it less conducive to star formation in some regions, while enhancing it in others by compressing molecular clouds. The merger will dramatically reshape how gas is distributed across the two galaxies. Gravitational forces will pull gas toward the core regions, creating dense central reservoirs that fuel intense star formation. At the same time, some gas will be flung outward into tidal tails, long streams of stars and gas that stretch out from the merging galaxies. While the collision will ignite a burst of star formation, it will also hasten the depletion of gas reserves. Star formation consumes vast quantities of gas, and the feedback effects from massive stars and supernovae further eject gas into intergalactic space. Over billions of years, the new galaxy, Milky Way, will transition from a vibrant star-forming system to a quieter, gas-poor galaxy dominated by older stars. This transition mirrors the life cycle of other galaxies in the universe, where mergers initially invigorate star formation but ultimately lead to quiescence. The depletion of gas marks the end of an era of growth, leaving behind a galaxy filled with the remnants of its starburst past. Advanced computational simulations offer a window into what might occur during the Milky Way Andromeda collision. By modeling the behavior of gas, stars, and dark matter, these simulations predict the formation of starburst regions, the movement of tidal features, and the long-term evolution of the merged galaxy. Observations of other colliding galaxies, like the antennae galaxies, provide real-world analogues that validate these predictions. Infrared and X-ray telescopes in particular have been instrumental in studying starburst regions and the heating of gas during mergers. These observations inform our understanding of the upcoming collision, highlighting the critical role that gas dynamics will play in shaping the future of the Milky Way and Andromeda. Observational evidence of galactic collisions elsewhere. One of the most iconic examples of a galactic collision is the antennae galaxies, also known as NGC 4038 and NGC 4039. Located approximately 45 million light-years away, these two spiral galaxies are locked in a dramatic embrace. Their collision has created long tidal tails, arcs of stars and gas flung out into intergalactic space by gravitational forces. These tidal tails are littered with clusters of newly formed stars, birthed from the compression of gas clouds during the galaxy's interaction. The antennae galaxies are a visual testament to the power of galactic mergers. Observations from the Hubble Space Telescope have revealed starburst regions, areas of intense star formation triggered by the collision. These regions are hundreds of times more active than typical star-forming areas in isolated galaxies, demonstrating how mergers can ignite a cosmic firestorm of creation. Closer to home, at just 31 million light-years away, the Whirlpool Galaxy, M51, and its smaller companion, NGC 5195, offer a stunning example of gravitational interaction. The Whirlpool Galaxy's spiral arms appear to be stretching toward its companion, creating a visual spectacle of tidal forces at work. The gravitational pull of NGC 5195 has distorted the Whirlpool's arms, enhancing their brightness and triggering waves of star formation. Infrared observations from the Spitzer Space Telescope have provided insights into how gas is funneled into the central regions of the Whirlpool Galaxy, fueling starburst activity. This interaction is a scaled-down version of what we might expect when the Milky Way and Andromeda eventually collide, providing a window into our galaxy's distant future. The Tadpole Galaxy, UGC 10214, is another striking example of a galactic collision. Its defining feature is a long, luminous tail stretching over 280,000 light-years, formed by the gravitational interaction with a smaller galaxy. This tail is populated with bright star clusters, evidence of the intense star formation triggered by the collision. Observing the Tadpole Galaxy gives astronomers a unique perspective on how smaller galaxies can dramatically reshape their larger counterparts during a merger. The Cartwheel Galaxy, located 500 million light-years away, owes its unusual appearance to a collision with a smaller galaxy that passed directly through its center. The resulting shock waves created a rippling effect, forming the galaxy's characteristic ring structure. This collision has triggered star formation in the outer ring, while the inner regions exhibit complex patterns of gas and dust redistribution. The Cartwheel Galaxy exemplifies the diverse outcomes of galactic mergers, depending on the geometry and scale of the collision. Stephan's quintet, a compact group of 5 galaxies, provides a chaotic view of multi-galaxy interactions. Located about 300 million light-years away, this group showcases shock waves, high-energy X-ray emissions, and intergalactic gas collisions. The gravitational interactions within the quintet have stripped stars and gas from their host galaxies, creating an intricate web of tidal streams. Observing such complex dynamics helps scientists understand how galaxies evolve in crowded environments. While large galaxy mergers capture the imagination, dwarf galaxies also play a crucial role in cosmic interactions. The Sagittarius dwarf galaxy, currently merging with the Milky Way, has left behind tidal streams of stars visible in the night sky. These streams serve as a living record of the ongoing interaction and illustrate how larger galaxies grow by consuming smaller ones. The Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, are also interacting with the Milky Way, creating the Magellanic Stream, a trail of gas stretching across the southern sky. These interactions provide a smaller-scale preview of the dynamics involved in larger galactic mergers. Understanding galactic collisions requires observations across the electromagnetic spectrum. Optical telescopes like Hubble capture the visible light emitted by stars, revealing the structural changes in galaxies. Infrared telescopes, such as Spitzer, peer through dust to observe hidden star-forming regions. X-ray observatories like Chandra detect high-energy phenomena, including shock waves and hot gas clouds generated by collisions. For example, X-ray observations of Stephan's quintet have revealed intergalactic shock waves created by gas clouds moving at speeds of up to 6 million kilometers per hour. These shock waves are a vivid reminder of the violent energy unleashed during galactic interactions. Advances in computational astrophysics have allowed scientists to simulate galactic mergers with remarkable accuracy. These simulations use real-world data, such as the mass, velocity, and composition of galaxies, to model their interactions. By comparing simulation results with observational evidence, astronomers can test theories about the phases of galactic mergers and predict outcomes, such as the formation of tidal tails and starburst activity. The observed collisions of galaxies like the antennae, whirlpool, and tadpole offer critical insights into the fate of the Milky Way and Andromeda. These examples help astronomers predict the phases of the merger, from the initial approach and tidal disruptions to the eventual formation of a new galaxy. Observations of other galactic collisions provide a glimpse into the long-term transformation of our cosmic neighborhood, reminding us that the universe is a dynamic and ever-changing place. Unveiling cosmic transformations. Galactic evolution in action. Galactic mergers are among the most transformative events in the universe. When two galaxies collide, their gravitational forces intertwine, reshaping both into a larger, often more complex entity. Over billions of years, this process of hierarchical merging has been the engine driving the formation of massive galaxies. Spiral galaxies, like our Milky Way, often transform into elliptical galaxies through these mergers. The collision disrupts their orderly spiral arms, redistributing stars into more random, spheroidal arrangements. Observations of giant elliptical galaxies at the centers of clusters reveal their histories as products of numerous past collisions. These structures, colossal in scale, owe their existence to countless smaller galaxies consumed over cosmic time. Larger galaxies devour their smaller neighbors, absorbing their stars and gas. This process can be seen in our Milky Way today as it consumes the Sagittarius dwarf galaxy, its tidal forces stretching the smaller galaxy into long streams of stars. This cosmic snacking adds to the mass and complexity of the larger galaxy, steadily building its grandeur. Galactic mergers are not just about stars. They are also about the raw materials of creation. When galaxies collide, their gas and dust collide too, triggering waves of star formation. Within these newly ignited stars, nuclear fusion forges heavier elements like oxygen, iron, and carbon. When these stars die in supernovae, they scatter their enriched material into the intergalactic medium. This enrichment process is crucial for the evolution of the universe. Heavy elements, or metals in astronomical terms, are essential for forming planets and the complex chemistry needed for life. Observations of tidal streams, rivers of stars and gas pulled from merging galaxies, show evidence of metal-rich material being flung into intergalactic space, seeding future generations of stars and galaxies with the ingredients for complexity. Even today, we can trace the metallicity of stellar populations back to the history of galactic mergers. Older stars, formed before major collisions, tend to have lower metallicity, while younger stars born during or after mergers show higher concentrations of heavy elements. This ongoing enrichment is a cornerstone of cosmic evolution. Galactic collisions do not occur in isolation. They are part of a larger narrative involving galaxy clusters and the cosmic web. Galaxy clusters, the most massive structures in the universe, owe their formation to the repeated merging of smaller groups of galaxies. At the heart of these clusters lie central galaxies, often giant ellipticals, formed through the accumulation of many smaller galaxies. The cosmic web, a vast network of filaments and voids, provides the stage for these mergers. Galaxies within filaments are drawn together by gravity, their paths guided by the underlying dark matter. Mergers along these filaments contribute to the growth and evolution of the universe's most colossal structures. In this way, the smallest scales of galactic dynamics are intimately connected to the largest scales of the cosmos. The dramatic increase in star formation that results from galactic collisions is one of their most noticeable effects. New stars are formed more quickly when gas clouds in merging galaxies collapse due to their own gravity. Starburst galaxies are characterized by their intense luminosity, which is produced by large stars with relatively short lifetimes. This burst of activity is both a creation and a consumption of resources. While starbursts contribute to the growth of a galaxy's stellar population, they also deplete its reservoirs of gas. Over time, the galaxy exhausts its ability to form new stars, becoming quenched. This transition from a vibrant, star-forming galaxy to a quiescent one is a key phase in galactic evolution. Mergers between gas-rich galaxies are particularly dramatic, creating dense molecular clouds where stars form in abundance. Observations of galaxies like the antennae galaxies reveal regions of intense star formation, giving astronomers a glimpse of what might happen when the Milky Way and Andromeda collide. Galactic mergers are not just theoretical, they are observable in spectacular detail. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of colliding galaxies. From the iconic antennae galaxies to the Whirlpool galaxy's dramatic interaction with a smaller companion. These observations provide real-time examples of the processes shaping the universe. Computer simulations complement these observations, allowing astronomers to recreate the dynamics of mergers and predict their outcomes. These models have been instrumental in understanding the stages of galactic collisions and the factors that influence their results. Stellar migration during galactic collisions. When galaxies collide, the cosmos becomes a stage for one of the most mesmerizing and complex dances of matter and energy. Stars, planets, and interstellar material become players in an elaborate gravitational reshuffling. Stellar migration, the movement of stars during these colossal events, emerges as one of the most captivating phenomena. This intricate process unfolds over billions of years, with stars being nudged, scattered, or even ejected, creating new galactic structures and revealing profound insights about the mechanics of the universe. Gravitational interactions during a galactic merger can turn stars into cosmic wanderers, launching them out of their galaxies at incredible speeds. Known as hypervelocity stars, these objects achieve escape velocity and are flung into intergalactic space, severing their ties with their home galaxies forever. During the impending collision between the Milky Way and Andromeda, it is estimated that millions of stars could face this fate. These expelled stars become valuable to astronomers, as their trajectories can be traced backward, offering a glimpse into the gravitational forces and dynamics of the merger. Galactic collisions often produce shell-like formations of stars, a phenomenon resulting from the gravitational pulling and stretching of stellar populations. These elegant arcs and concentric shells act as evidence of past mergers, appearing like luminous ripples around galaxies. In galaxies such as NGC 3923, these structures persist as fleeting reminders of the collision process. The Milky Way-Andromeda merger is likely to produce similar shells, providing temporary spectacles of light and movement before dissipating into the broader galactic structure. The collision between the Milky Way and Andromeda will not simply blend the stars of both galaxies, but will dramatically redistribute them across the newly formed galactic structure. Stars from the dense central regions of each galaxy may migrate outward, while stars from the fringes could be drawn inward by the gravitational pull of the merging cores. This redistribution is a key feature of galactic evolution, with entire populations of stars relocated to form a unified, though dramatically altered, galactic ecosystem. Before the collision, stars in the Milky Way and Andromeda follow predictable orbits influenced by the gravitational centers of their galaxies. However, as the galaxies merge, these orbits will be disrupted, resulting in complex and chaotic stellar motions. Some stars will adopt elongated elliptical orbits, while others may follow looping or irregular paths. These shifts in stellar kinematics provide astronomers with invaluable data, allowing them to model the intricate gravitational interplay that defines galactic mergers. The phenomenon of hypervelocity stars represents one of the most striking outcomes of galactic collisions. These stars are accelerated to extraordinary speeds during gravitational interactions, often involving close encounters with dense clusters or massive stellar groups. As the Milky Way and Andromeda collide, astronomers expect a significant increase in hypervelocity stars, many of which could become intergalactic travelers. These stars are not only scientific curiosities, but also serve as natural laboratories for studying extreme gravitational dynamics. The stars residing in the halos of the Milky Way and Andromeda are typically older and less active than their galactic core counterparts. During the collision, these halo stars will migrate outward, blending into the faint, extended structures of the newly formed galaxy. Observing the behavior of halo stars during this process offers a unique perspective on how galactic edges evolve and interact during a merger. As stars migrate during the collision, gravitational forces may temporarily group them into clusters, creating transient pockets of heightened brightness. These fleeting clusters, though short-lived compared to stable globular clusters, provide a snapshot of the chaotic yet beautifully structured nature of stellar migration. They serve as markers of the galaxy's transformation, highlighting regions of intense gravitational interaction. Stars carry the chemical signatures of their origins, and the collision between the Milky Way and Andromeda will mix these chemical profiles on a galactic scale. By analyzing the metallicity and composition of stars, astronomers can trace their migrations and identify their original locations within their parent galaxies. This blending of chemical signatures will create a mosaic that tells the story of the galaxy's merger, preserving the history of their individual evolution. Ripples and waves generated by gravitational forces during the collision act as invisible hands, redistributing stars across the galactic plane. These ripples transfer energy through the galactic disk, nudging stars into new positions. Similar phenomena observed in other merged galaxies, such as NGC 474, provide a framework for understanding how these wave-like patterns will influence the Milky Way-Andromeda collision. These ripples, though transient, leave a lasting impact on the structure of the resulting galaxy. The Milky Way already hosts remnants of past galactic mergers in the form of stellar streams, like the Sagittarius stream. These streams, composed of stars torn from smaller galaxies, offer a glimpse into the aftermath of galactic collisions. As the Milky Way and Andromeda merge, similar streams will likely form, weaving through the newly created galactic structure and serving as records of the collision's gravitational ballet. Dwarf galaxies within the local group will also feel the effects of the Milky Way-Andromeda merger. These smaller galaxies may lose stars to the gravitational pull of the merging giants or have their internal structures disrupted. The ripple effects of the collision could scatter dwarf galaxy stars across the larger galactic remnant, further blending the local group into a unified structure. During the chaotic phases of the collision, gravitational alignments may form linear chains of stars. These chains, though temporary, highlight the gravitational forces at work and serve as visual indicators of specific stages in the merger. Their brief appearance adds a dynamic and awe-inspiring element to the stellar migration process. Regions of active star formation, known as stellar nurseries, will face significant upheaval during the merger. As these regions are disrupted by tidal forces, young stars may be scattered into new environments, altering their developmental paths. Conversely, some migrating protostars may find themselves in denser regions, sparking unexpected bursts of star formation. Binary stars, bound together by gravity, face unique challenges during galactic mergers. While some binaries will remain intact, others may be separated by tidal forces, sending their components on diverging paths. Those that survive the collision may end up in entirely new orbits, showcasing the resilience and fragility of these stellar partnerships. The migration of stars during the merger will also affect their planetary systems. Gravitational disturbances could destabilize planetary orbits, causing planets to be ejected or to collide with their host stars. In some cases, planets might be captured by new stars, forming entirely new systems. This dynamic reshuffling underscores the fragility of planetary environments in the face of galactic-scale events. Open star clusters, loose groupings of stars, will not escape the gravitational chaos of the merger. Some clusters may be torn apart, scattering their stars across the new galaxy, while others might migrate intact, forming new associations in the evolving galactic structure. Observing these clusters provides valuable data on how gravitational forces act on smaller stellar groupings. Migrating stars experience shifts in their surrounding environments, from changes in radiation exposure to interactions with interstellar material. These changes can accelerate or alter the star's evolutionary paths, leading to unexpected properties. Analyzing these anomalies sheds light on how stars adapt to new conditions, offering insights into the interplay between stellar migration and evolution. This cosmic choreography of stellar migration reveals the profound interconnectedness of the universe. Each star, whether ejected, scattered, or integrated into new structures, tells a story of motion, transformation, and the unrelenting forces that shape galaxies. Light echoes and post-collision luminosity. As the Milky Way and Andromeda converge, their collective brilliance will escalate, producing a galaxy that could rival the luminosity of some of the most radiant star systems in the observable universe. This amplified glow is not merely a matter of stars combining forces. It is the synergy of countless individual light sources interacting on a galactic scale. The sheer density of stellar regions will lead to a heightened glow that can serve as a beacon for neighboring galaxies and far-reaching observers in the cosmos. Some regions of this merged galaxy will host particularly intense brightness due to the compression of gas clouds into star-forming regions. Imagine clusters of new stars so dense and luminous that their light outshines entire galactic arms. This increased luminosity will make the Milky Way galaxy a focal point for astronomers, not just for its scale, but for its unprecedented brightness. Interstellar dust will take on a starring role in this galactic merger. As the two galaxies mix their interstellar media, dust particles will scatter and refract light, creating vast and intricate patterns across the new galaxy. These patterns will act like nature's own light shows, painting the night sky with shifting halos and trails of diffused brightness. The interaction of light with this dust won't just be visually stunning, it will provide valuable scientific insights. By studying how light is scattered and absorbed, astronomers can infer the size, composition, and distribution of the dust, revealing secrets about the galaxy's histories. For planets within this system, these patterns might create celestial spectacles akin to prolonged cosmic sunsets, illuminating the skies with vivid, multicolored displays. As gravitational forces eject rogue stars from the Milky Way galaxy, they will drift into intergalactic space. These solitary stars, though few in number compared to the billions remaining in the galaxy, will continue to emit their faint light. To a distant observer, these rogue stars will appear as scattered pinpoints of light in the cosmic void, faint reminders of the galactic upheaval that cast them adrift. Some of these rogue stars may travel with small clusters of companions or gas remnants, creating miniature systems that glow faintly against the backdrop of intergalactic darkness. For astronomers, tracking these stars could offer insights into the dynamics of the merger and the forces at play during such colossal collisions. Perhaps the most visually striking result of the Milky Way-Andromeda collision will be the starburst regions. These zones, ignited by the compression of gas and dust during the merger, will become prolific nurseries for young, hot stars. Unlike typical star formation, which occurs gradually, starbursts are dramatic and intense, producing clusters of stars that shine far brighter than their surroundings. It is possible for starbursts to produce superstar clusters, which are extremely dense collections of stars with luminosities comparable to those of smaller galaxies. Astronomers from all across the cosmos will be drawn to these areas, which will serve as beacons. The tale of Milcomeda's genesis will be repeated for millions of years after the fact, because the light from these clusters will continue to travel. Huge shadows will be produced throughout the galaxy as light from freshly generated stars interacts with thick gas clouds. The patterns formed by these shadows, which are invisible to the human eye, will be discernible via powerful telescopes. By charting these shadows, astronomers will be able to piece together the new galaxy's three-dimensional structure, shedding light on Milky Way's material distribution like never before. Imagine a celestial equivalent of light beams piercing through fog, with every shadow and highlight telling a story about the density, composition, and motion of the gas and dust in the galaxy. These features, though transient on cosmic scales, will offer a fleeting glimpse into the complexity of galactic evolution. As gas clouds collide and merge, they will give birth to new nebulae, vast glowing clouds of ionized gas illuminated by nearby stars. These nebulae will shimmer in vibrant hues of red, blue, and green, depending on the chemical composition of the gas. Some of these nebulae will be transient, dissipating after millions of years, while others may persist as iconic features of the Milky Way galaxy. For planetary observers within the galaxy, these nebulae will dominate the night sky, offering breathtaking views that change over millennia. Each nebula will act as a cosmic gallery, showcasing the results of the galactic collision and the ongoing processes of creation and destruction. Light echoes, created when bursts of light reflect off interstellar dust, will act as natural time capsules of the merger. These echoes will ripple outward from supernovae and other luminous events, providing a way to trace the history of the collision. By studying these echoes, astronomers can piece together the sequence of events that unfolded during the merger, much like archaeologists reconstruct ancient civilizations from ruins. Unlike direct observations of the galaxy, light echoes allow us to look into the past, offering a unique perspective on the processes that shaped Milky Way. These echoes will serve as living records, preserving the memory of the collision for future generations of astronomers. Charged particles released during the merger may interact with magnetic fields to produce galaxy-scale auroras. These auroras, much like those on Earth, will result from the excitation of particles as they collide with gas in the interstellar medium. Unlike terrestrial auroras, however, these displays could span light years, creating vast curtains of light that ripple across the galaxy. The colors and patterns of these auroras will vary depending on the chemical composition of the interacting particles, offering a kaleidoscope of cosmic hues. Observing these phenomena could provide insights into the interplay between charged particles, gas, and magnetic fields during galactic mergers. As stars, gas, and dust are flung into intergalactic space during the collision, they will create long, faint streaks of light that stretch beyond the boundaries of the merged galaxy. These streams, visible as ethereal arcs, will be some of the most delicate yet beautiful relics of the merger. For neighboring galaxies, these intergalactic streams will serve as visible reminders of the grand collision, offering a glimpse into the scale and impact of galactic interactions. These streams might also act as pathways for future exploration, leading astronomers to study the outer reaches of Milky Way and its connections to the broader universe. For any civilizations existing within the merging galaxies, the night sky will undergo a dramatic transformation. Over millions of years, the familiar constellations will dissolve and reform as stars shift positions. The increased luminosity of the galaxy might even create conditions where nights are never completely dark, with a persistent twilight illuminating planetary surfaces. These changes will not only alter the visual landscape of the sky, but could also influence the culture and mythology of any civilizations witnessing the events. The stories told by these observers, inspired by the celestial dance unfolding above, could become as enduring as the merger itself. For galaxies far removed from the Milky Way and Andromeda, the collision will be a spectacle visible across cosmic distances. Alien astronomers, equipped with advanced telescopes, might study the event to gain insights into their own galactic histories and futures. The light from the Milky Way merger will travel for billions of years, reaching distant civilizations long after the events have unfolded. Implications for the local group. The Triangulum Galaxy, or M33, is one of the most interesting characters in this cosmic opera. Triangulum is dangerous because it is the third biggest galaxy in the local group. Recent findings, including tidal distortions and stellar material exchange, point to its gravitational interaction with Andromeda. Triangulum will most certainly be dragged into the gravitational tug-of-war when the Milky Way and Andromeda combine, Simulations indicate that Triangulum may eventually be absorbed into the newly formed galaxy, often referred to as Milkomeda. However, its fate is not guaranteed. Depending on its orbital path and velocity, Triangulum might remain a distinct satellite of Milkomeda, contributing its stars and gas to future waves of star formation. This process would mirror what we see in other galactic mergers, where smaller galaxies are either consumed or incorporated as satellite systems. The collision of the Milky Way and Andromeda is not an isolated event. It is part of a larger narrative of galactic evolution within the local group. As the two largest galaxies merge, they will dominate the gravitational landscape, effectively reshaping the local group into a single, unified structure. This process may resemble what we observe in other galaxy groups that have coalesced into massive elliptical galaxies. The local group's barycenter, or gravitational center, will shift dramatically as the merger unfolds. The combined mass of Milkomeda will draw in smaller galaxies, potentially leading to further mergers. Over billions of years, the local group could transition from a collection of distinct galaxies into a single, massive galactic system, bound by gravity and stripped of its individuality. The Large and Small Magellanic Clouds, two of the Milky Way's most prominent satellite galaxies, will also be affected by the merger. These galaxies are already losing material to the Milky Way through the Magellanic Stream, a trail of gas that stretches across the sky. As the Milky Way and Andromeda collide, the gravitational forces at play will likely intensify, accelerating this process. The Magellanic Clouds could serve as a reservoir of gas for the newly formed galaxy, fueling bursts of star formation during the merger. Alternatively, they might be entirely consumed, their stars and gas becoming part of Milkomeda's stellar population. In either case, their contributions will leave a lasting imprint on the merged galaxy, enriching its composition and altering its structure. During the Milky Way-Andromeda merger, these tidal interactions will become even more pronounced. New streams will form as stars and gas are redistributed across the group. As galaxies merge, their stellar populations undergo significant changes. Existing stars are displaced from their original orbits, often migrating to the outer regions of the newly formed galaxy. At the same time, the compression of gas clouds during the collision triggers intense periods of star formation, creating new generations of stars. In the local group, this process will not be limited to the Milky Way and Andromeda. Smaller galaxies caught in the gravitational crossfire may also experience bursts of star formation as their gas is compressed by tidal forces. Over time, the local group's stellar population will become more homogeneous, blending the distinct characteristics of its member galaxies into a single, unified system. The impending Milky Way-Andromeda collision offers a unique opportunity to study galactic evolution on a grand scale. By observing similar mergers in other parts of the universe, such as the antennae galaxies, astronomers can refine their models and make more accurate predictions about the local group's future. These observations reveal that galactic mergers are not chaotic, destructive events, but rather natural stages in the life cycle of galaxies. They show how interactions between galaxies can lead to the redistribution of stars and gas, the formation of new structures, and the eventual creation of massive elliptical galaxies. The local group's transformation is not an anomaly. It is a microcosm of the universe's larger story. Across the cosmos, galaxy groups are merging to form larger structures, driven by the inexorable pull of gravity. The Milky Way-Andromeda merger is a local chapter in this universal narrative. The role of dark energy in the Milky Way-Andromeda collision. The local group, the cosmic neighborhood containing the Milky Way, Andromeda, and their smaller galactic companions, is governed by gravity rather than the expansive pull of dark energy. In the broader universe, dark energy drives galaxies apart, accelerating the expansion of cosmic space. However, within the gravitational boundaries of the local group, the attraction between galaxies overpowers this universal outward push. This localized dominance of gravity creates an exception to the overarching trend of the universe's expansion, allowing the Milky Way and Andromeda to move toward an inevitable collision. While the Milky Way-Andromeda merger is a gravitational phenomenon, it cannot be entirely separated from dark energy's pervasive influence. Dark energy, often described as the driving force behind the universe's accelerating expansion, prevents galaxy clusters from coalescing into larger structures. In contrast, smaller, gravitationally bound systems like the local group remain largely unaffected by dark energy's pull. This interplay reveals a layered structure to the cosmos, where the laws governing galactic behavior shift depending on the scale of observation. A critical player in the collision is dark matter, which forms vast halos around galaxies like the Milky Way and Andromeda. These halos act as gravitational anchors, binding galaxies together and directing their motion. In contrast, dark energy exerts a subtle but relentless outward pressure, pulling space itself apart on a universal scale. Understanding how these two invisible forces, dark matter and dark energy, interact is key to predicting the precise timeline and dynamics of the impending collision. Simulations suggest that the dense dark matter halos of the Milky Way and Andromeda will play a significant role in guiding the two galaxies toward one another. Even as the universe expands due to dark energy, the halo's immense gravitational influence ensures that the galaxies remain on a collision course. The galaxies' beginning velocities and trajectories affect the time of the Milky Way-Andromeda merger, which is anticipated to occur around 4 to 5 billion years from now. Over billions of years, these characteristics may be somewhat altered by the large-scale effect of dark energy, especially around the local group's periphery. The impact on this particular collision is small, but learning about the local group reveals how dark energy and gravity interact in universes like ours. Precise measurements of Andromeda's motion, including its transverse velocity, rely on data from advanced telescopes like the Hubble Space Telescope and Gaia. These observations refine our understanding of how dark energy influences galactic motion within gravitationally bound systems. Central to understanding dark energy's role is the Hubble constant, a measure of the universe's expansion rate. Variations in this constant across different cosmic regions, an area of ongoing scientific debate, affect predictions about galactic collisions. Accurate measurements of the Hubble constant could illuminate how dark energy interacts with gravitationally bound systems, providing a clearer picture of the Milky Way-Andromeda timeline. Recent advancements in observational techniques, such as gravitational lensing and Type Ia supernova measurements, are narrowing the uncertainties surrounding the Hubble constant. These findings indirectly enhance our understanding of dark energy's subtle influence on local galactic dynamics. Dark energy's accelerating expansion isolates galaxy clusters over time, effectively severing their interactions with other regions of the universe. The local group, currently part of the larger Virgo supercluster, will eventually become gravitationally disconnected from other clusters as dark energy drives them beyond reach. This isolation underscores the importance of the Milky Way-Andromeda merger as one of the last major interactions within the local group. Future cosmic epochs will see the local group evolve into a single, dominant galactic entity, surrounded by a vast expanse of empty space. This transformation highlights the dual roles of gravity and dark energy in shaping the ultimate fate of cosmic structures. The collision between the Milky Way and Andromeda will ignite bursts of star formation as gas clouds collide and compress. However, dark energy indirectly influences this process by contributing to the long-term depletion of gas in galaxies. As the universe ages, the availability of cold gas for star formation diminishes, a phenomenon known as galactic quenching. In the context of the Milky Way-Andromeda merger, this means that while initial bursts of star formation will occur, the resulting galaxy will eventually transition into a quieter, elliptical form with minimal star-forming activity. This transformation mirrors broader trends observed in the universe, where dark energy's dominance leads to a gradual decline in star formation. Theoretical models and simulations play a crucial role in understanding dark energy's effects on galactic collisions. Advanced simulations, incorporating both dark matter and dark energy dynamics, provide a window into how galaxies evolve over billions of years. These models reveal the intricate balance between local gravitational interactions and the broader influence of cosmic expansion. One key finding from these simulations is the stability of dark matter halos, even as dark energy accelerates the universe's expansion. This stability ensures that galaxies like the Milky Way and Andromeda remain gravitationally bound despite the universe's broader trajectory. Dark energy's role in the Milky Way-Andromeda merger extends beyond physics, offering profound philosophical reflections. As humanity observes the forces shaping the cosmos, dark energy serves as a reminder of the universe's impermanence and ceaseless change. The merger, framed within the context of dark energy's influence, symbolizes the delicate balance between creation and destruction, stability and transformation. The interplay of dark energy and gravitational forces challenges humanity to view the universe as a dynamic, interconnected system. Understanding these forces not only deepens our knowledge of cosmic phenomena, but also reshapes our perspective on existence within an ever-evolving cosmos. Despite significant advancements, many questions about dark energy remain unanswered. What is its true nature? How does it interact with matter and gravity on both local and universal scales? The Milky Way-Andromeda merger, while primarily driven by gravity, offers an opportunity to probe these mysteries further. Future missions, such as the Nancy Grace Roman Space Telescope, aim to shed light on dark energy by studying its effects on cosmic structures. The impending collision of the Milky Way and Andromeda represents a natural laboratory for studying dark energy's role in shaping the cosmos. By observing this event and comparing it to similar collisions elsewhere in the universe, scientists can refine theories about the interplay of gravity, dark matter, and dark energy. The ever-changing cosmos. Galaxies, often perceived as eternal and unchanging, are far from permanent. The Milky Way itself, with its spiral arms and luminous stars, is a product of billions of years of evolution, collisions, and mergers. But like all things in the universe, it is temporary. The gravitational forces that govern the cosmos ensure that galaxies are always on the move, constantly interacting, colliding, and reshaping one another. Gravity is the architect of this impermanence. It pulls galaxies toward each other, driving them into eventual mergers that obliterate their original forms. The gas and dust within galaxies, essential for star formation, are not infinite. Over time, this fuel is consumed, leading to the gradual dimming of stellar activity. Even the stars themselves, which seem to define the identity of a galaxy, have finite lifespans. They are born, shine brightly for eons, and eventually collapse into remnants like white dwarfs, neutron stars, or black holes. Dark energy adds another layer to this impermanence. As the universe expands at an accelerating pace, galaxies are being driven farther apart, ensuring that future collisions will become increasingly rare. Eventually, even the Milky Way's merged form with Andromeda, tentatively named Milkomeda, will drift into isolation, its light fading against an ever-darkening cosmic backdrop. Despite the destruction they bring, galactic mergers are not the end. Instead, they are a form of cosmic renewal. When galaxies collide, their vast gas clouds are compressed, sparking intense bursts of star formation. New stars are born from the chaos, lighting up the merged galaxy and giving it a fresh identity. This cycle of destruction and creation underscores the dynamic nature of the cosmos. The process of renewal is not limited to star formation. Collisions also redistribute matter across the galaxy, forming tidal tails and streams of stars that stretch into the surrounding void. These features, remnants of a once separate existence, eventually settle into the structure of the new galaxy. Over billions of years, the merged galaxy takes on a new shape, often elliptical, becoming a testament to the transformative power of cosmic collisions. Historical observations of galactic mergers, such as the antennae galaxies, provide glimpses into this process. These celestial interactions show us that while individual galaxies may cease to exist, their components continue to contribute to the evolving story of the universe. From the debris of collisions come new opportunities for star systems, and perhaps even planets, to form. For humanity, the scale of these events is almost incomprehensible. Galactic mergers unfold over billions of years, timescales that dwarf the entire history of human civilization. The transient nature of galaxies challenges our understanding of permanence, forcing us to confront the vast difference between cosmic and human timescales. Yet, this understanding also enriches our perspective. The Milky Way, which seems immutable in the night sky, is just one chapter in an ongoing cosmic narrative. Recognizing its impermanence can help us appreciate the fleeting beauty of the stars and the extraordinary chance we have to observe them during our brief existence. Change is not confined to galaxies. The entire universe is in flux, governed by forces like gravity, dark energy, and thermodynamics. The expansion of the universe ensures that galaxies are not static but are constantly moving, interacting, and evolving. Even the largest structures, such as galaxy clusters and cosmic filaments, are part of this ever-changing landscape. Entropy plays a significant role in this evolution. The second law of thermodynamics states that systems naturally progress toward greater disorder. In the cosmic context, this means that galaxies, stars, and other structures will eventually dissipate their energy. Over unimaginably long timescales, the universe will reach a state of maximum entropy, often described as the heat death, where all activity ceases, and only faint remnants of matter remain. The cycles of creation and destruction seen in galactic collisions are part of a broader cosmic rhythm. The universe has been shaped by the interplay of these forces since the Big Bang. From the formation of the first stars to the assembly of galaxies, each stage of cosmic evolution builds upon the remnants of what came before. The transient nature of galaxies carries profound philosophical implications. It challenges the idea of permanence, not just in the cosmos, but also in human thought. Many philosophical traditions, such as Buddhism, emphasize impermanence as a natural law. The universe's constant state of flux mirrors this principle, offering a cosmic perspective on the impermanence we experience in our own lives. Interconnectedness is another theme that emerges from this understanding. Just as galaxies are connected through gravity and shared histories, so too are humans connected to one another and to the universe itself. The elements that make up our bodies, carbon, oxygen, nitrogen, were forged in the hearts of stars, linking us to the cosmos in a tangible way. Accepting impermanence can also be empowering. It reminds us that change is inevitable and that endings often lead to new beginnings. In the case of galactic collisions, the end of individual galaxies gives rise to new formations, new stars, and new possibilities. This cycle of renewal echoes the potential for growth and transformation in our own lives. Understanding the impermanence of galaxies is more than a philosophical exercise. It is a scientific endeavor that deepens our knowledge of the universe. By studying galactic collisions and their aftermath, scientists gain insights into the processes that shape cosmic structures. These observations also inform our understanding of the universe's history and its future trajectory. The impermanence of galaxies inspires wonder and curiosity. It invites us to marvel at the universe's complexity and to ponder our place within it. While the collision of the Milky Way and Andromeda may seem distant, it is a testament to the dynamic and interconnected nature of the cosmos. It reminds us that change is not an end but a beginning, a chance for renewal, discovery, and growth. Galactic collisions and the future of astronomy. Galactic collisions are more than just a gravitational tug-of-war. They are cosmic laboratories where the forces of creation and destruction play out on a grand scale. When galaxies collide, Their stars rarely smash into each other due to the vast distances between them, but the gas clouds and dark matter halos surrounding these galaxies tell a different story. These collisions trigger dramatic bursts of star formation as gas clouds compress, creating hotbeds of activity where new stars are born in rapid succession. In this context, galactic collisions provide unparalleled insight into the formation of elliptical galaxies. Spiral galaxies like the Milky Way often transform into elliptical galaxies when they merge with other massive systems. This metamorphosis occurs as the graceful spirals give way to a more chaotic and spherical shape, driven by the gravitational reshuffling of stars and gas. Observing these events helps scientists understand how the universe's most massive galaxies came to dominate cosmic structures. Another vital discovery from galactic collisions is the redistribution of heavy elements, metals like oxygen, carbon, and iron, throughout the cosmos. When galaxies merge, their interstellar gas is churned and enriched, spreading these essential elements across vast regions. This cosmic mixing is key to understanding the chemical evolution of the universe and the availability of elements necessary for the formation of planets and life. To unravel the mysteries of galactic collisions, astronomers rely on cutting-edge technology. Instruments like the James Webb Space Telescope, JWST, offer unprecedented clarity in observing these phenomena, especially in infrared wavelengths that reveal the hidden regions of star formation. JWST is already poised to deliver data on the dense, dusty regions of colliding galaxies, shedding light on the processes driving their dramatic transformations. Meanwhile, the upcoming Nancy Grace Roman Space Telescope will complement JWST by mapping large-scale galactic interactions and measuring cosmic expansion with incredible precision. These two observatories, working in tandem, promise to revolutionize our understanding of galactic mergers and their role in the universe's evolution. Gravitational wave observatories, like the planned Einstein Telescope and Cosmic Explorer, are also set to play a crucial role. When supermassive black holes at the centers of colliding galaxies merge, they generate ripples in space-time that can be detected by these advanced instruments. These observations offer a new way to study galactic mergers, providing insights into events that are otherwise invisible. To investigate local and faraway galactic interactions in greater detail, ground-based extremely large telescopes, ELTs, are under development. They will provide a sharper view of merging galaxies because scientists will be able to examine individual stars, gas clouds, and black holes because of their remarkable resolution. Beyond observational tools, computer simulations have become indispensable in understanding galactic collisions. These simulations model how galaxies interact over millions or billions of years, predicting everything from the initial approach to the final merger. By incorporating data from telescopes and gravitational wave observatories, these simulations create dynamic, evolving models that help scientists anticipate what will happen when galaxies, like the Milky Way and Andromeda, collide. The use of artificial intelligence and machine learning has further enhanced these simulations. AI algorithms analyze vast datasets, identifying patterns and anomalies that might otherwise go unnoticed. This synergy between human ingenuity and computational power accelerates our understanding of galactic evolution. Galactic collisions are not isolated events. They are part of a larger narrative of cosmic evolution. When galaxies merge, they contribute to the formation of even larger structures, such as galaxy clusters and cosmic filaments. These massive formations, stretching across millions of light-years, are the scaffolding of the universe. Studying galactic collisions helps scientists understand how these large-scale structures developed over time. Another thing such collisions show is that the cosmos is always recycling. Mergers cause new stages of cosmic history by redistributing and reusing gas, dust, and stars. This endless cycle of creation and annihilation is a basic feature of the universe, resonating at sizes ranging from stars to galaxies. How galaxy collisions relate to cosmic background radiation is one of the most fascinating things about them. These light signals from the early cosmos give hints about the conditions that molded the universe billions of years ago, as they hold fingerprints of the earliest galactic encounters. Connecting the dots between the early cosmos and the present requires an understanding of these relationships. As we study galactic collisions, we also refine our understanding of dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter halos, which envelop galaxies, play a crucial role in guiding their motions and interactions. Observing how these halos influence collisions provides indirect evidence of dark matter's presence and properties. Dark energy, on the other hand, drives the universe's expansion. While this expansion might seem to keep galaxies apart, the gravitational pull of dark matter can overcome dark energy's effects on smaller scales, leading to collisions like the Milky Way Andromeda merger. By studying these events, scientists gain insights into the interplay between dark energy, dark matter, and gravity. Investigating galactic collisions is an undertaking that spans the entire globe. From visible light, observatories on Earth and in space record many facets of these occurrences. The Square Kilometre Array, SKA, is one example of an international partnership that is combining forces to study the biggest structures in the cosmos and to track the dynamics of hydrogen gas in merging galaxies. Multi-messenger astronomy, which combines observations across different wavelengths and phenomena, has also become a cornerstone of galactic collision research. By integrating data from telescopes, gravitational wave detectors, and neutrino observatories, scientists can piece together a more comprehensive picture of these events. Looking ahead, the next generation of telescopes and missions promises to deepen our understanding of galactic collisions. Proposed space observatories like the Large UV Optical Infrared Surveyor, LUVOIR, aim to study these events across a wide spectrum, revealing details that current instruments cannot capture. Advancements in X-ray and infrared telescopes will allow scientists to probe the hot gas and dusty regions of merging galaxies, providing insights into star formation, black hole activity, and gas dynamics. These instruments will also help address lingering questions about the timing and outcomes of galactic mergers. In the end, galactic collisions are a testament to the universe's dynamic and ever-changing nature. They remind us that the cosmos is not static, but a symphony of forces and interactions that shape everything from individual stars to the largest cosmic structures. Through the study of these monumental events, we gain not only a better understanding of the universe, but also a deeper appreciation for our place within it. Supermassive black holes and the merger. These enigmatic objects, millions to billions of times the mass of our Sun, hold the galaxy's innermost secrets, acting as both its anchor and its ultimate sculptor. As the Milky Way and Andromeda prepare for their inevitable collision, the interaction between their central supermassive black holes, Sagittarius A star, and Andromeda's M31 star, will set the stage for one of the most extraordinary chapters in cosmic history. Let us unravel the intricate dance of these colossal entities and the impact their convergence will have on the new galaxy to come. At the core of the Milky Way lies Sagittarius A star, a relatively quiet supermassive black hole with a mass of about 4 million suns. While Sagittarius A star may seem dormant compared to more active black holes, it occasionally flares to life, releasing bursts of X-rays and radio waves as it feeds on surrounding matter. Meanwhile, Andromeda's central black hole, known as M31 star, dwarfs Sagittarius A star, weighing in at over 100 million solar masses. Unlike its counterpart, M31 star has been far more active in its galactic lifetime, devouring gas and stars at a pace that has left telltale trails of high-energy emissions. The stark difference in size and activity between these two black holes adds an intriguing layer to the story. When their host galaxies collide, these titans will embark on a cosmic journey of interaction, disruption, and ultimately, unification. As the Milky Way and Andromeda spiral toward each other, their supermassive black holes will initially remain at the centers of their respective galaxies. However, as the galaxies merge, the black holes will begin to sense each other's gravitational pull. Over millions of years, they will draw closer, entering a phase known as a binary black hole system. In this phase, the black holes will orbit one another, their immense gravitational forces creating ripples in the very fabric of space-time. These waves, predicted by Einstein's theory of general relativity and recently detected by observatories like LIGO, will grow stronger as the black holes close the distance. The final moments of their interaction will see the two black holes spiraling inward at incredible speeds, radiating gravitational waves so powerful that they could be detected across the universe. When the black holes collide, their event horizons will merge, and their masses will combine to form a single, even larger, supermassive black hole. This new black hole, potentially exceeding 150 million solar masses, will become the gravitational heart of the merged galaxy, often referred to as Milky. Its immense gravity will shape the orbits of stars and gas, anchoring the galaxy's new structure. The merger will release an enormous amount of energy, some of which will be carried away by gravitational waves. These waves, in turn, could impart a recoil to the new black hole, potentially displacing it from the exact center of the galaxy. Such a phenomenon, known as a gravitational wave kick, has been observed in other merging galaxies, offering a tantalizing glimpse into the cosmic aftermath of black hole collisions. The gravitational waves produced during this merger will tell a story etched in spacetime itself. These waves will carry information about the masses, spins, and orbital dynamics of the merging black holes. Future space-based observatories like the Laser Interferometer Space Antenna, LISA, will be well equipped to detect these low-frequency waves, providing an unprecedented window into the final stages of the Milky Way Andromeda collision. During the merger, gas and dust from the colliding galaxies will be funneled into the centers, feeding the black holes and triggering intense periods of activity. As the black holes consume this material, they will ignite as active galactic nuclei, AGNs, releasing enormous amounts of energy in the form of radiation and relativistic jets. These AGNs will shine brighter than the combined starlight of the entire galaxy, making Milky visible across cosmic distances. This burst of activity will have profound effects on the surrounding environment. Radiation and outflows from the AGNs will heat and ionize nearby gas, quenching star formation in the central regions of the galaxy. This feedback mechanism, observed in other merging galaxies, plays a critical role in shaping the evolution of galaxies over time. The gravitational interplay between the merging black holes will create tidal forces capable of disrupting nearby stars. Some stars will be drawn into the black hole's accretion disks, where they will be torn apart and consumed, releasing energy as they spiral inward. Others will be ejected from the galactic core entirely, becoming hypervelocity stars traveling at extraordinary speeds through the galaxy, or even escaping into intergalactic space. The interaction will also create star streams and tidal tails, long, luminous trails of stars and gas that stretch across the galaxy. These features, seen in other galactic mergers, will provide a visible record of the Milky Way and Andromeda's union. Our understanding of supermassive black hole mergers has been greatly enhanced by theoretical models and computer simulations. These simulations, powered by advancements in computational astrophysics, allow scientists to visualize the complex interplay of gravity, gas dynamics, and dark matter during galactic collisions. They also help predict the behavior of black holes as they spiral toward their inevitable union. Observations of other merging galaxies provide real-world analogues for what will happen when the Milky Way and Andromeda collide. For example, the galaxy NGC 6240, which hosts a pair of merging supermassive black holes, offers a glimpse into the future of our own galaxy. Instruments like the Event Horizon Telescope and space-based observatories will continue to refine our understanding of these cosmic phenomena, preparing us for the moment when our own galaxy becomes a part of this grand cosmic narrative. Despite our growing knowledge, many questions remain. What happens at the very moment two event horizons merge? Could the final stages of the collision reveal new physics, such as insights into quantum gravity or the true nature of singularities? And how will the merged black hole influence the evolution of Milkomeda over billions of years? Cosmic cycles, the eternal dance of galaxies. Galactic collisions are far from chaotic catastrophes. They are engines of cosmic renewal. When galaxies collide, their gas, stars, and even dark matter are redistributed across vast regions of space. This process seeds the formation of new stars and planets, giving rise to entirely new systems. The Milky Way itself has absorbed smaller galaxies over billions of years, enriching its own resources and laying the foundation for future star formation. These collisions serve as the universe's way of recycling, ensuring that materials don't stagnate but are continually repurposed for new cosmic creations. Galaxies, much like living organisms, undergo cycles of birth, growth, and eventual transformation. Spiral galaxies, with their elegant arms, often transition into elliptical galaxies after a collision. This metamorphosis is driven by the gravitational interplay during mergers, which disrupts the ordered motion of stars and gas. Over time, these chaotic interactions settle into more stable configurations, giving rise to new galactic structures. The elliptical galaxies that emerge carry the combined legacies of their progenitors, a testament to the life cycles of these cosmic giants. At the core of every galactic interaction is gravity, a relentless force that orchestrates the motion of galaxies across vast cosmic distances. Gravity pulls galaxies together, driving the inevitability of their collisions. It governs not just the timing of these events, but also their outcomes. The gravitational interplay between two galaxies determines how their stars are scattered, how their gas clouds interact, and what structures emerge from the chaos. Without gravity, the cosmic dance would cease to exist, and the universe as we know it would lose its dynamic rhythm. Galactic collisions are not isolated events, but part of a larger cosmic framework. These interactions contribute to the formation of galaxy clusters, superclusters, and even the vast cosmic filaments that make up the universe's large-scale structure. Every merger adds to this interconnected web, redistributing matter and energy in ways that shape the universe's architecture. Over billions of years, these processes have created the sprawling networks of galaxies that define the observable universe. Through the lens of advanced telescopes, astronomers have observed countless galactic collisions across the cosmos. Iconic examples, like the Antennae galaxies and Stephan's Quintet, provide stunning visual evidence of the dynamic nature of these events. These observations reveal tidal tales, streams of stars flung into space by gravitational forces, and regions of intense star formation. Each collision tells a story, offering clues about the physics of galactic interactions and their role in cosmic evolution. The aftermath of galactic collisions often includes the expulsion of intergalactic gas, which plays a crucial role in future cosmic cycles. This gas, enriched with heavy elements from stars, drifts into intergalactic space, where it may later be drawn into new galaxies. This ongoing redistribution ensures that the cycle of creation and destruction continues, connecting galaxies across vast distances and sustaining the flow of cosmic material. Collisions between galaxies take place over far longer periods of time than anything humans can imagine, billions of years to be exact. We are reminded of the immensity of cosmic time by these delicate, gradual interactions, where epochs, not lifetimes, are the units of measurement for change. The astounding lengths of time required by these processes make us question our own transience and put our place in the cosmos into perspective. During a galactic collision, enormous amounts of kinetic energy are redistributed among the interacting systems. This energy drives the motion of stars, gas, and even dark matter, creating new configurations and dynamic motions. The energy dissipated during these events helps stabilize the resulting galaxy, allowing it to settle into a new equilibrium. Understanding this energy transfer is key to unraveling the physics behind galactic mergers. The cosmic cycles of galaxies mirror natural cycles on Earth, from the changing of seasons to the regeneration of ecosystems. Just as ecosystems rely on the recycling of nutrients, the universe relies on galactic collisions to redistribute resources and sustain its dynamic balance. This parallel invites us to see ourselves as part of a much larger interconnected system, where cycles of renewal are a universal constant. Galactic collisions embody the dual forces of creation and destruction, dismantling old structures while paving the way for new formations. Stars are scattered, gas clouds are compressed, and galaxies are transformed. But the cycle never ends. This interplay of forces ensures that the universe remains dynamic, constantly evolving and reshaping itself over billions of years. How gravity waves shape galactic structures. During mergers, gravitational waves, though imperceptible in our daily lives, are silent and unyielding forces that shape the universe's grand design. Their influence extends far beyond dramatic black hole collisions or neutron star mergers. They are pivotal players in galactic evolution, subtly orchestrating the intricate dance of galaxies. Unlike the dramatic bursts of energy from stellar mergers, gravitational waves generated during galactic collisions are long, slow, and persistent. These waves emerge from the shifting gravitational center of colliding galaxies as they spiral toward one another. This movement, driven by the enormous mass of billions of stars, gas clouds, and other material, creates a symphony of ripples that propagates across the fabric of space-time. These waves don't fade into the background. They actively shape the evolving structure of the colliding galaxies, guiding them toward their final forms. Galaxies carry immense kinetic and potential energy as they move through space. When two galaxies begin to merge, the interaction produces gravitational waves that act as cosmic energy regulators. These waves help dissipate excess energy, allowing the galaxies to slow down and settle into a stable state. Without this mechanism, the merger process could be chaotic and prolonged, with galaxies orbiting and tearing each other apart indefinitely. The energy transfer through gravitational waves effectively accelerates the merger's completion, ensuring a smoother transition to a unified structure. Gravitational waves emitted during mergers affect more than just the galaxies themselves. The surrounding environment, including satellite galaxies and interstellar gas, also experiences their influence. For instance, a nearby dwarf galaxy caught in the gravitational wave's ripple might be nudged closer to the merging system or destabilized, leading to its absorption or disruption. This cascading effect highlights how galactic mergers reverberate throughout the cosmic neighborhood, influencing systems far removed from the main event. Gravitational waves' capacity to imprint spacetime with a lasting impression, a phenomenon called gravitational wave memory, is one of its most intriguing features. Spacetime is squeezed and stretched in certain ways during a merger, and these distortions may be preserved even after the waves have gone. A galaxy's star paths, or the geometry of the merging structure, may undergo small but long-lasting changes as a result of this. The event's history is encoded into the cosmos itself via these persistent impressions, which function as a cosmic signature. The role of gas clouds in galactic collisions is often discussed in terms of star formation, but gravitational waves add a new layer to this narrative. As these waves move through interstellar gas, they create regions of compression and rarefaction, akin to ripples on a pond. These density fluctuations can either trigger bursts of star formation by compressing gas into critical densities or inhibit it by dispersing gas too thinly to coalesce. This dynamic interplay underscores the indirect yet powerful influence of gravitational waves on stellar birth. At the centers of merging galaxies, gravitational waves contribute to the chaotic yet purposeful migration of mass toward the core. Stars, gas, and even compact objects like neutron stars or rogue planets are subtly guided by these waves into new configurations. This process often results in the formation of dense central regions or even superstructures like galactic bulges. These gravitational waves are not merely background noise, they are active participants in defining the heart of the merged galaxy. Satellite galaxies, the small companions to larger systems, often bear the brunt of a merger's gravitational turbulence. These satellites are pulled, stretched, and sometimes stripped of their stars and gas, creating tidal streams that stretch across the heavens. Gravitational waves generated during the merger amplify these effects, redistributing material from satellites into the larger system. This redistribution plays a critical role in building the halos and extended structures of the resulting galaxy. During a galactic merger, interstellar gas doesn't simply collide and compress. It is shaped and redistributed by gravitational waves. In some cases, gas is funneled into the central regions of the galaxies, fueling bursts of star formation or even active galactic nuclei. In other instances, the waves scatter gas into the outer reaches, forming vast diffuse halos. This redistribution impacts the chemical composition and evolution of the galaxy for billions of years. When galaxies merge, the gravitational waves they produce have an impact much beyond the bounds of the merging galaxy. Intergalactic gas clouds and smaller galaxies nearby can experience the reverberations. These waves may gently change the paths of nearby galaxies, bringing them closer together or sending them in other directions. This may eventually cause secondary contacts, which in turn might set off a cascade of cosmic events within the cluster of galaxies. Galactic mergers don't occur in isolation. They are part of the vast, interconnected structure known as the cosmic web. Gravitational waves generated during these mergers propagate through the filaments of this web, reinforcing or disrupting its structure. While these effects are subtle, they contribute to the evolution of the universe's largest scale features, linking individual galactic events to the broader tapestry of cosmic evolution. On the smallest scales, gravitational waves might even influence planetary systems within merging galaxies. These waves could alter the orbits of distant objects like comets, asteroids, or even exoplanets, potentially triggering new bombardment events or migration patterns. While the effects are minuscule compared to the galactic scale, they demonstrate the pervasive reach of gravitational waves in shaping cosmic environments. An interesting theory is that adjacent galaxies might be stimulated to interact by gravitational waves caused by a large galactic merger. It is possible that these waves will push nearby systems into closer proximity, which might cause them to merge or interact with one another. A single galaxy merger might have a multiplicative effect on the cosmos if this feedback loop causes a chain reaction inside a galaxy cluster. Gravitational waves from galactic mergers play a role in the long-term evolution of the universe. By redistributing mass and energy, they contribute to the gradual growth of larger, more complex structures. Over billions of years, this process transforms galaxy clusters, superclusters, and even the cosmic web itself, weaving an intricate story of creation and transformation. Within merging galaxies, stars are often thought of as passive participants in the collision. However, gravitational waves subtly influence their trajectories, redistributing them into new orbits or even flinging some into intergalactic space. This redistribution contributes to the final structure of the merged galaxy, creating patterns and features that reflect the wave's influence. Gravitational waves from galactic mergers might also carry echoes of earlier cosmic events. These waves propagate through space-time, encountering and interacting with relics of the early universe. By studying their patterns, astronomers might uncover clues about the universe's infancy, adding a new dimension to our understanding of cosmic history. Our capacity to detect and understand gravitational waves will increase at an exponential rate as new, more sophisticated detectors are developed. We will be able to study galactic mergers in unprecedented detail thanks to space-based observatories like LISA, which promise to provide new insights into their stately and beautiful dance. Rather than being transient signals, gravitational waves are ever-present forces that alter the cosmos at all sizes. It controls everything from the dispersion of gas and star formation to the ultimate shapes of whole galaxies. The ultimate fate of the Milky Way. As the galaxies collide, their gravitational forces will intermingle, distorting their forms into tidal bridges and tails of stars, gas, and dark matter. Over time, this chaos will settle, erasing the distinct identities of the Milky Way and Andromeda, leaving behind one vast, unified galaxy. The individual histories of these two galactic titans will become inseparably intertwined, with the remnants of both galaxies visible only in the composition of the stars and gas in the merged entity. This transformation will not happen overnight. The collision between the Milky Way and Andromeda will play out over billions of years in a series of stages. The first phase, already underway, is the gravitational attraction between the two galaxies. Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In roughly 4 billion years, the two galaxies will begin their first physical encounter, marked by tidal forces pulling and stretching their outer edges. Streams of stars will be ripped from both galaxies as they start to interpenetrate. During this initial collision, Andromeda and the Milky Way will pass through each other, temporarily creating a chaotic, distorted structure. But gravity will pull the two back together again, leading to subsequent encounters over hundreds of millions of years. Eventually, the two will coalesce into a single, stable galaxy, but this process will take as long as 10 billion years to fully settle. As the Milky Way and Andromeda collide, the Sun and its planetary system will also be affected. Currently located about 27,000 light-years from the Milky Way's center, the Sun's position relative to the galactic core will shift dramatically. The collision will disrupt the Sun's orbit, possibly flinging the solar system into a completely new region of the merged galaxy. Some models suggest that the solar system could end up much closer to the new galactic core, while others predict it may be cast farther out into the galactic outskirts. Regardless of the exact outcome, the night sky as seen from Earth will change dramatically. The collision will light up the sky with brilliant views of Andromeda's stars and gas clouds, followed by chaotic streams of material as the two galaxies merge. Over billions of years, the spectacle will fade as the new galaxy stabilizes. During the merger, the collision of gas clouds from both galaxies will ignite a period of intense star formation. These starbursts, fueled by the compression of interstellar gas, will produce clusters of new stars, illuminating the chaotic galaxy with brilliant light. However, this phase will be short-lived on cosmic timescales. Once the available gas is exhausted, star formation will slow and eventually cease. The new galaxy, likely elliptical in shape, will become dominated by aging stars. The gas and dust that sustain stellar nurseries will be consumed or ejected into intergalactic space. The galaxy will transition from a vibrant, dynamic structure to a more static, red and dead galaxy, populated primarily by older, cooler stars. When the two galaxies merge, their central black holes will spiral toward each other, eventually coalescing into an even more massive black hole. This event will release immense gravitational waves, rippling across the fabric of space-time, a cosmic phenomenon that may one day be detectable by advanced observatories. The merged black hole will become the dominant gravitational force at the center of Milky, shaping the motion of stars and gas in its vicinity. During the merger, the influx of material into the black holes could trigger episodes of activity, turning them into active galactic nuclei that emit intense radiation and jets of energy. The fate of the Milky Way illustrates the cyclical nature of galaxies. Galactic collisions and mergers are a fundamental aspect of the universe's evolution, driving the growth of larger and more complex structures. The Milky Way itself is the product of countless smaller mergers throughout its history, as evidenced by star streams and globular clusters that trace the remnants of consumed galaxies. While the Milky Way's identity will be lost in the merger, its legacy will live on in the stars, gas, and dark matter that form Andromeda. The newly merged galaxy will continue to evolve, influenced by gravitational interactions with other members of the local group, including the Triangulum galaxy and smaller dwarf galaxies. Over time, these interactions could lead to the formation of an even larger cosmic structure, eventually encompassing the entire local group. As we journey through the cosmos together, exploring the breathtaking inevitability of the Milky Way and Andromeda's collision, one thing becomes clear. The universe is as much a place of endless questions as it is of stunning answers. This is just one chapter in the grand story of existence, one that we are privileged to observe, study, and share. If this exploration of galactic collisions and cosmic evolution sparked your curiosity, imagine what more there is to uncover. The universe is vast, and our collective quest to understand it is only just beginning, so let's keep the conversation alive. Feel free to like this video, subscribe to the channel, and turn on notifications so you never miss another dive into the mysteries of the cosmos. Thank you for watching.